Hello everyone, welcome to today's webinar. Thank you for joining. I'm Jesper Karlström. I worked at Prover now since 2008. I'm in charge of engineering at Prover, meaning products and services. So what I will do today is to show you the full Prover Trident process, as we call it, which is the solution for how to automate the process of signaling design automation. I will also give some recommendations in the end of this demonstration if you want to change your process and make it more automated. And there will be a questions and answers session in about 30 minutes from now. So feel free to post questions in the text box. You do so and we will read them during the webinar, but no one else will see the questions. We'll bring them up in the end in the questions and answers session. So you can prepare by posting questions. Okay, so let's get going. Our process that we will discuss today is not tailored for any specific system, any specific area of the world or so, but made in such a way that it should be possible to use this process for any kind of signaling systems, any kind of signaling principles. So for the sake of demonstration, we just came up with some simple demo signaling principles. And to give some examples of this, let's look at the 5 aspects we use for signals. There is an upper light of the signals we use that signals the main speed. It can be red, yellow, or green, depending on if it's proceed unrestricted. Then there is a lower light that is used only when the upper one is green, and the lower light simply tells you the color of the next main signal. So it's a kind of distance signaling. Okay, very simple. As far as we know, there are no such signals in the world anywhere, but they could potentially be anywhere. So the idea is that anyone should be able to follow these principles, although no one should recognize them as their own. The content of this demonstration will be in 3 chapters. First, we'll look at the specific application process. It consists of configuring a station with mock-up signaling principles, doing some simulation, both interactive and scripted simulation, doing formal verification and code generation. In the configuration is a process where you enter the layout of the station, but also sometimes some tables with extra information. For this demonstration, we have no tables, so it will only be the layout of the tracks. Simulation is the usual way to find errors or omissions. Formal verification is mathematical proof that the system fulfills certain safety requirements. And code generation is the simple process where you construct the code that should be loaded onto the platform. So this process works for very many different hardware platforms. It has been used for platforms that are mainly designed to be manually programmed, like Microlock or Westrace, but the process has also been designed for platforms that use more what should I say, general purpose languages such as C. The certification process then is a standalone formal verification process where you can prove that the safety requirements are fulfilled again. This has already been done in the specific application process as a way for the engineers to check that the system is safe. But to get some independence, we offer a specific tool that is developed in a different way and according to all Senelec norms necessary to reach SIL 4. Finally, I will mention a bit of the generic application process. It's not the main topic of this webinar, but I will show a few examples of how signaling principles are encoded in this logic language we use, and also what happens if you, by purpose, introduce a few errors in the code, just to show you how these errors are discovered in the simulation and formal verification activities. Okay, prepare for the demonstration. Let me start the application. This is the Windows application we use for doing signaling design automation. It's made in Windows because Windows is the most commonly used platform for engineering in the railway sector. But to reach independence, the certification process I will mention later is done with on a Linux platform. But to start a project with from scratch, we need to choose the signaling principles. So we press this new project thing and we choose which principles to use. And I will use today demo 302. So it's a demo package we have of version 302, our latest version. We can call it just project 1 and we put it on the desktop, here to make it easy to find. So the project will be a folder where all sorts of data, and some data is created now when I create a project, but some other data will be created as configuration data and generated code and so on. In these principles, in this package, demo package, there is a choice of a few symbols that should be available. They turn up here to the left, and these are the ones that we will use to configure the layout of this station. Then this package name demo of version 302, it specifies that certain other packages should be loaded as dependencies. So all these packages are listed here with versions on the fingerprints. And these fingerprints allow this program to discover if there are any changes in the packages that are unintentional or intentional, but nevertheless we can find changes made, which is a good feature to ensure integrity, of course. Okay, let's do this. And to make it the layout will work like in the painting program, drawing tracks and adding track circuits and so on. Because we will draw quite a lot now, I use the repeat new object feature, which makes it possible for me to just click once on the symbol I want to use and then draw several of the same kind. So let me do for you a simple meeting station. First a track like this, then we need a track at the top and some switches down to the main track, like here. So I say switch, and in the British railway terms that is called point, but Americans normally use switch as a term. Then we need some joints. So pick out joints. We can choose names if we like, but I will not use the names, so we just go for the default ones here to save some time. Okay, this is our meeting station now. We have some track circuits between the joints. So as you can see, it's fairly quick to configure the station like this. Then we add also directions. I will not use the name, so I go for the defaults again. And a location object, that's essentially only a name of the station. And finally some signals. And now there are signals of the kind that I mentioned when we started. And it doesn't matter if I put them to the left or the right, it's the red little dot that defines where they end up logically. Okay, and now I save because I think I'm actually done. And now you can see the different symbols up here. This is for interactive simulation. This is for a simulation of predefined tests. This is for formal verification. You can create some documents here and you can generate some code. Before we can do this, the computer needs to compute the precise interlocking principles for this station. So it will do that using the track layout I just made here, but also all the generic application principles that have been pre-entered. So these are the ones that are stored in the package demo 302, which we chose from the beginning. Now these principles have been read into the system and the station has been configured using this drawing. So we can start an interactive simulation to look at what happens. This is a simulator window. I normally put that on a different screen, but now I have only one for this webinar, so let's just minimize it and look at this canvas again. You can see that the signals now have are lit up here, and we can do things like requesting a route. So we simulate an input from the office system, requesting a route. You could probably see the little point or switch moving here. We can simulate the request for it moving to the left or one moving to the right, like this. The green arrow here denotes a locked route, and you can see that this signal has turned to yellow. So let's also request a route for the entrance here. It's gray, meaning that it has been stored in the interlocking. And now we can see what happens if a train leaves the station. So we put one here and we can choose run train en route. And it will move the occupancy here from the station and out on the line. And when the train leaves the station, the switch here throws, the new route locks, and then this route eventually disappears. And we can let this train enter the station again, like this. Okay, so this is the interactive simulation where you can play around and test your interlocking. Very handy, but also very traditional in the sense that you have all the traditional problems of being sure that you actually covered all the cases. So one thing that has been introduced to help is that you can also script test cases. So these are predefined also in the package we loaded, demo 302. So it's in this case, there are 3 tests here for main routes, and there is also 1 test for all the ways that you can traverse the interlocking from one end to another. So if you open here, you can see that this is only 1 test, but here there is one test for each little route here, and 1 test for each of these routes, and so on. So if I press run, I run all the tests for all the instances, and we can see that everything is green here. If it would be any problem, one of them would turn up red. Then we can do form verification. So it's safety requirements that also have been predefined, a number of safety requirements like this, and you can formally verify that the interlocking fulfills them by pressing run. And it runs a model checker and concludes here that those 336 safety requirements that we used were fulfilled. This is the model checker ProverSL CE that we also use and sell as a separate tool, but in ProverILOC it's built in to verify that the design has been follows all the safety requirements. Okay, let me stop the interactive simulation like this. Then we have now tested and verified, and it's time to create the code. So I press here, and it will write all the code to a folder inside this project folder. IL is for interlocking. There's a simulation folder, but I think in here the source code is actually stored. So this one has been generated based on, it's C code in this case, and it has been based on the mathematical model of the interlocking that has been constructed by the program. So this is how the generated C code looks, and it can be now compiled and put on the platform. Okay, I can also do a few other things that will help us when we move move on with the certification process, I can generate some certification data. That's a dump of all the configuration data that we need for this station, because when we run formal verification, you need in one way or another to ensure that the configuration data we entered here is actually correct. So this data needs to be reviewed. And it's not very trustworthy to review it directly on screen, because it's Windows and you can never know that everything is rendered as is here. So it's text dump here where you can actually review that the configuration data has been correct. You can also look at the safety properties. They are stored here in the language HLL, which is a formal verification language that is used quite a lot in the railway business and also a few other areas. It's based on predicate logic with some sorts. I will not show a lot of these files, but anyway, here they are. We can also dump the HLL model, so it's not, it's like the C code, but it's not C. It's just a mathematical model of the system. This can be used if you want, for example, to verify that the generated C code actually respects the mathematical model. So you can use formal verification to compare the mathematical model with the generated C code to ensure that no problems were introduced. Okay, so let me go back here to this and quickly look at what we did for the SA process. We did the following: configure the station. That was only drawing the track layout because this is a simple demo and I wanted it to be quick. But usually you also need to complete the number of tables with configuration data. It can be, for example, timer values, but it can also be, if you don't want generic definitions of protection objects or other things, you might want to be able to enter in the configuration tables which objects to use as protection and similar things. I showed also simulation, which here is both interactive simulation and scripted simulation. In my opinion, it's very important to have good simulation support in order to discover unfortunate choices early. So even if everything is according to specifications, it might be the case that some choices of how to actually draw the tracks and so on are unfortunate because of the signaling principles. It might prevent some simultaneous routes that you actually want and so on. So it's very useful to find such omissions early to do interactive simulation. And also for the scripted ones, but scripted ones are more useful for running many test cases. So generic test cases that you want to run for all instances, for example, while interactive simulation is more useful for playing around and understanding the system. I ran also the formal verification module. Within a second, you can prove hundreds of requirements if the design is made like this, made for being provable by formal verification. And in the end, we did some code generation, just pushing a button to get the code dumped, as C code in this case. Let's continue with the certification process. I must leave this and show you. I put the project here on the desktop. We have the generated C code. We have also certification data that we dumped, and we have the HLL code. So if we have a standalone certification process that wants to prove that the C code generated fulfills the safety requirements and is equivalent to the HLL code that we dumped, then we need to send this to the certification program. So what we offer is a web-based tool for doing this. So I zip all these things so they end up in an archive, just to have fewer files. And then let's go here to Prover Cloud Apps, where there are many different tools, but I will use this Prover Certifier for the demonstration. Demo webinar. This is only for to remember what this was about. And then we choose the file, and we choose to take the one from this one we just created, the zip file. And then we run the certification. What happens now is that this one is the one we created, and it has been scheduled. So because there might be many customers that use this service at the same time, and one thing is run after another. So sometimes it's up to a minute before this work has been started. But when this has been done, you can just do something else because you will be emailed when the certification run has completed. Now the job is running, and we need to wait a bit to see the results. Okay. The certification flow is like this. We usually use two sources of code. So in this case, it was the C code, and it was the HLL code model dump. The C code could be something generated, like we did today, generated C code, or it could also be imported code. And imported code is used when code has been manually written. For example, if there is no system like the one we used now with an automated process for generating code, but something manually written, we can still import that code into Prove, Certify, and check it. The source 2 of the code has sometimes been compiled binary code and sometimes a logical code model as it is today. The safe requirements are those that are briefly showed, that are written in HLL, and they are the same for each installation. So if you make, for example, a line of 10 or 20 stations, you have the same safety requirements for all of them, although the configuration data is different for each station. You need to review them or ensure that they are correct in some way, but it can be done at the generic application level. So you don't have to redo this process for each station. You do it only once when the safety requirements have been written. Configuration data, on the other hand, must be reviewed at the specific application level because the configuration data is different for each station. The process was just shown. You collect all the relevant files in a zip archive. We did this, then we ran Prove, Certify on Prove Cloud Apps. Or if you don't want a web-based solution, you can just transfer the files to the Linux computer and run the tool from there. What we have not done today is to review the safe requirements and configuration data. So as you saw, running the formal verification is very quick, but you need also to ensure that you actually prove the right safety requirements and that the configuration data you have been using is the correct one. And this is not covered by formal verification. This you need to ensure in some other way. I want to stress also that using a web interface or a Linux computer might seem a bit disruptive, but it's not really, because you use ProViloc over and over again while you configure and you try different configurations. You can do your formal verification in ProViloc. So only when everything is done, you run this on the standalone sign-off verification tool on a web interface or a Linux computer, and that's something you do only once. So it's not really very problematic. Let us look at this now, if it has been completed. Yes, it says it's complete. And we have here the log from this run. And we can scroll down the log to see the end. It says that it was successful here. You can also download this report or download simply a short summary of all the files with their checksums and the result of the run, and so on. Okay, let's move on. I covered everything more or less that I wanted to cover, the specific application process and the certification process. This was the main topic of today's webinar, but I promised also that I would show a few files just to give you some insight on how the generic application is actually written, because it's not it's a rather unique idea that you write the generic application in a logic language and define all the principles on this level, rather than doing it either manually by manual coding as in older and smaller interlockings, or you do it as part of the generic product. That's also quite common. Okay, so let me show this. I'll bring up a few examples. I can do like this. Oops, sorry. What I wanted to look at is the design package 3.0.1. So as you see, this is something Unix-like. It's actually a Cygwin that I use on Windows, simply because I think it's more convenient to look at the files in this way. But if I look at, for example, the implementation of point here, if I make a few changes to the design. So for example, if I use a very typical error, we have here the logic for when to throw a switch to the left, and here's the logic for when to throw it to the right. Let us look at this, and I evaluate all the symbols here. Then I will, by purpose, introduce an error to show you how to discover error. Okay, this symbol is a not symbol. So through to the left, it checks that not this object in itself, that is the point, that it's not locked. That's the point. It's a not symbol. This is an and symbol. So it actually checks 5 things. It's not supposed to be locked. It's not supposed to already be placed to the left. It's not supposed to have a request from the HMI to be thrown to the right, because that's the point of throwing it to the left if there is a request to throw it to the right, and so on. It's not supposed to be requested by any route to be thrown to the right. And then the final condition here is that there should either be a left request from the HMI, so the human machine interface, or there should be a request by the route to throw to the left. So as you see, the logic for throwing to the left is symmetric to the logic for throwing it to the right. But then, as you might be aware, a very common mistake is when you make this kind of programming with copying something from left to right, that you forget to replace left here by right. So let's introduce this and pretend that this typical error was made. So it's left in both cases here. This should of course be right, but now someone has been a bit lazy, made the copying and forgot to change this to the right. Okay, so save this. I cannot save because it's open in this one. It's actually protected if you use, I need to close it, if you use a package that has a certain you cannot save any changes if it's open in the program. But let me open it again now after having it. Sorry, like this. I open it here. The first thing it doesn't open it. I mentioned the integrity before. Requested root should be able to ask a switch to be thrown to the right. It does not work anymore. So if you look here on this one, if I request this root, then this root will request this one to go to the left, and this should still work. So I try it. Yes, it works. It was thrown to the left. Then I release this one. And then I request this route instead. And we can now expect that this will not work because this switch needs to be thrown to the right, but the design doesn't work anymore. If I throw it to the right manually, it should work. So we'll do like this, because I didn't remove anything about the manual throwing. So by manually throwing the switch to the right, it works, and then the root locks. Now I could demonstrate this because I knew exactly what I did, but pretending that we didn't know that, we will probably not find this. But by running the simulator, you immediately find some test cases that do not work here. So if we open this one, for example, you can run the test case and you can see all the steps of the test case. It starts by waiting 60 seconds. It occupies the start track, requests the route, and then the route is supposed to be locked within 10 seconds, but this has failed. So it has stopped the simulation where it fails, which is actually more or less the case we tried, but in a different direction. So it tried to request this route, and this switch didn't throw. So this is a way that this can be, this error can be discovered by the scripted simulation. On the other hand, if we run formal verification, we probably will not find this error. This error is good, but it's not dangerous. If it doesn't violate any SIP requirement. If the switch is not thrown, then the route will not be locked and no signal will clear. So it's still a safe state. So this was an example of something that you do find with testing, but do not find with formal verification.
But could you please repeat the last question?
Probably construct something that is the opposite. So let me reverse this. This was supposed to be right. And then we do something else. If I look at the locking of the switch, I look for locked. Here it says that to lock a switch, it should happen if some track that this switch belongs to is not vacant. And this is an OR symbol. So some track is not vacant, and a few other things here, which I will not go into detail about. But the first thing is important to understand. Each switch here has an associated track. So this switch is supposed to be locked if this track is occupied. So let me start to just demonstrate this. If I put something on this track here, then I'm not able to throw this. It will simply not do anything. If I remove the occupancy, then I can throw the switch to the left. And this is the moving of the switch on an occupied track is prevented by this first line. So if I remove this line, I introduce a comment like this. So the line is removed. And then I reload everything. And we should look at the consequence of this. I reload the package now. I have reverted the old error, but I introduced a new one. So integrity is still, the integrity check fails again. Now run simulation. Now, if you think of it, what I did was I introduced a principle that says that if the track is occupied, then you cannot throw a switch. That is not 100% sure that we will discover by testing. And indeed, when I run all the tests, nothing discovers this, because all the tests that have been entered here are of the kind that it checks positive behavior. So if you request a route that you should have, then it will actually lock and you will be able to run a train and so on. It doesn't check negative things in this implementation. The formal requirements, though, make such checks, because it would violate a safety requirement not to lock the switch if it's occupied. So you can see here, after having run this, it's quick, by the way, it's less than a second, and most requirements pass here, but 2 fail. And if we click on them, we can see here, this requirement says a non-vacant switch must not alter its position. This is what is failed. And if I want to investigate it, I can double click on it. And it will produce for me a counterexample where this happens. So let's look at the counterexample. We can see here, now this is not very convenient because you cannot see the position, but you can still look at how this counterexample is violated. You can see at the time steps, 0 is the start of the system, 1 is after 1 step, and within 2 cycles it's possible to come to a case when the switch throws, although it's still not vacant here. So it's actually switch 1 that moves when S2 is not vacant. And if you look at them here on the layout, this is switch 1 and this is S2. Okay. So to sum up what we have been doing, I changed some signaling principles and investigated impact. Simulation showed how a small change turned out to have big unwanted impact. So by changing, introducing an error, replacing right by left, the consequences were big because many test cases failed by this change. So we had one example where simulation showed unwanted things, and one example where formal verification found this instead. We haven't been focused on the entire GA process today, but I would say that it's the generic application process when we work like this is not very different compared to any usual generic application development process. But please keep in mind that having an efficient generic application development process, to have that, you need to have a good specific application process. A few recommendations now before the questions and answers. By the way, feel free to just add questions, and Claes will sum up the questions we have. But first, a few recommendations if you want to use tools and automate your process. First, it's a good idea to integrate tools as much as possible. So there is an unfortunate tradition, at least in the railway sector, that you have a dedicated simulation room in the basement, and the engineers don't work with simulation. Engineers do development, and some tester makes the simulation in the end. We think it's very good during the development to actually run tests and formal verification on the desktop, on the laptop you're working with. So you know when you give the system to the tester that there will be no errors anymore. And in the same way, then, it's important to make these V&V tools available to all involved engineers, not only have one instance of this, but you should actually have these tools on everyone's laptop. The third is it's very important to bring your staff on board, because one common question we get is, what do we do with all the staff that are suddenly replaced by tools? And this, of course, is a general question of our modern society, but the solution is to let senior engineers work with the generic signaling principles, which is rather rewarding, I would say. And you can then keep the staff but do more projects. There is a strong need for railway in this world. And if you want to start a GA development process, you need to write some specifications for the line you want to signal. The object model first is a very precise specification of all the interfaces. And this is very important to do early on, because the interfaces will be used by all involved staff in these projects, developers, testers, and everyone that's supposed to contribute in some way with this. So this must be very precise. And the advantage of the object model is also that you don't need to know many details in order to be able to specify the object model thoroughly. It's more difficult with the design principles, because typically you want to develop and the system and investigate its work in a more agile way. So work with both the specifications and the development at the same time. So it's enough to start with the fundamental principles and then do the details on the way. For tests, it's a good idea to write scripted scenarios early to be able to work in a test-driven way and see that more and more scenarios are covered. And the same with safety requirements. If you write them early, then you can use formal verification to check that your system is safe. If you don't want to do this, we can help with this, or there are many other consultancy firms that can help with this. We can depart from example programs or drawings or whatever you have to do the specifications. It's good, though, if you have some expert that you can allocate to answer questions for this. Then the specifications have to be formalized. There is one specification for the design, one for the test, and one for the safety requirements. So if you want to do this, please just reach out and we can have a meeting via Skype or face-to-face, 1 to 2 hours, to review your current process and your current challenges. And this meeting should be enough for having a plan for how to increase automation in your process in the end. We can also set up inspiration workshops for your engineers if you want, or focus on the business case. Please just contact us about this. Okay, that's all I wanted to cover today. So, Claes, I'm curious to know if we have received any questions.
Yeah, and I would also like to, we did have some connectivity issues, I believe, minor ones. So we apologize for any disturbances of the sound that you might have heard. Just wanted to mention that we are aware of it, and yeah, we'll probably have it fixed by the next time. Really sorry about that. We did have some questions. I'd like to start with first one here. We don't have any documentation of our signaling principles today. What do we need to produce before we can start an interlocking design automation process?
As I mentioned, the object model needs to be fairly well specified. So it has to be produced, but it's not. You don't have to worry if you don't have it today. You will have to allocate an expert, and there are plenty of people that can help you write the specification based on examples you have and interviews with experts. So we can do it, for example, but I'm sure you can find others also.
All right. And let's see, we had another question here as well. What is the difference between the object model and the design?
Essentially, the object model doesn't say how to solve any things, only what inputs and outputs you do have. So, for example, in the object model might say that, okay, in our system we do have points, we have signals, we have track circuits. And for the points, they have those inputs, they have those outputs. The track circuits have those, and the signals have those. So not a lot to say about how these inputs are supposed to be fed or how these outputs are supposed to be energized, but only setting up the buffet of things to choose between. And then we can work with the signaling principles when we know what we have to work with. That's the point.
All right. Also have a question here. Is there possible to attend a course?
Right. We do courses quite often, actually. So just contact us and we'll arrange something for you, or we can tell you when the next one is available in your area.
All right. Okay. Let's see. We do have another here. Is there a way to develop specifications on the way, or do we need to write the specifications before we start developing?
I think you need to do the object model quite early, because our experience is that if you don't have the object model ready, then people will just starting to guess, because this kind of informal language we have seen is often it can be quite confusing when different terms turn out to actually mean the same thing, or when the same term actually turns out to mean different things in different contexts. So it's very important to have a clear object model with all the terminology from the start, or to start with this. And after that, I think the design can be done in a more detailed way.
All right. I think that was all questions that we had.
Okay, let me also say that if you are in the US, I see that some of you are from the US, please visit us at Minneapolis exhibition RSSI.
Yeah, we do have another question.
Okay.
Just came in here. Can you import or export track layout?
Yes, we can. We have been doing that for in many different formats, actually. Many customers have their own format, so we have seen different XML formats, for example, and we also offer a format you can use, which is called LCF, if you have the ability to export in a special format. It's very good because it's both machine readable and human readable, so it's easy to review that the data is correct or agrees with schematics or things.
All right. Well, I guess that that pretty much wraps this webinar up.
Yeah. So let me say again, we will exhibit at RSSI in Minneapolis next week. I travel on Saturday, actually. So visit us at our booth, 4422, simple number to remember. And there is an ARIMA conference at the same in the same area, the same day, where I will give a talk about a signaling modernization project at Stockholm Metro, which I think is a quite interesting reference project.
All right. We will send this to the presentation to everyone who has registered, so we will get this recording as well if you would like to see this webinar again. Otherwise, I think that's pretty much it. Okay. Thank you all for attending.
Thank you. Bye-bye.
And goodbye.